Okay, we're working on rotational stuff today. Rotational, circular motion, gravity included. Let's do it. A robot probe lands on a new uncharted planet. It has determined the diameter of the planet to be 8 times 10 to the 6 meters. It weighs a standard 1 kilogram mass and determines that 1 kilogram weighs only 5 newtons on this new planet. What must the mass of the planet be? Easy. So we're doing some gravity stuff here. F is equal to big G, big M, little m over r squared. We know the force of attraction is a whopping 5 times G, which is 6.67 times 10 to the minus 11 times big M for the mass of the planet times 1 because that's the mass of the weight. And the radius, this is the diameter, so the radius is going to be 4 times 10 to the 6 with a squared. Solve, solve, solve. Mass of the planet is going to be 1.2 times 10 to the 24 kilograms. Easy. And that's less than Earth, so U is okay. Earth is about 6 times 10 to the 24. Okay, blah, 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 blah. What is the acceleration due to gravity on this planet? Even easier, right? Because F is equal to ma. Maybe you've heard of this formula before. The force is 5. The mass is 1. What's the acceleration? Well, gee howdy. Acceleration is going to be a fifth, which is 0.2 meters per second squared. Express it in meters per second squared and in G's. G's. Okay. Well, hold the phone here. That's a fiver. Here's where that number comes from. So, expressed in G's, we're going to have 5 out of 9.8, or 10, as they like to do it. 5 out of 10 is a 1/2, so it's a 1/2 G. Ta-da. All right, next one. What is the average density of the planet? Density is equal to mass divided by volume. Well, we know the mass. The mass is 1.2 times 10 to the 24. The volume is going to be the volume of a sphere. So we're going to have 4/3 pi r cubed. What's the radius going to be? The radius is going to be half of the diameter one more time. So 4 times 10 to the 6. Bada bing, bada boom. Your density is going to equal about 4,474 kilograms per meter cubed. That makes sense. It's heavier than water, so it should work. Although it doesn't necessarily mean anything. Saturn is less dense than water. Anyways, let's look at the next one. The Earth has a mass of that and orbits the Sun in a lot of seconds at a constant radius. Wink, wink. So we're going to do some circular motion here and combine that with gravity. What is the Earth's centripetal acceleration around the Sun? Easy. Centripetal acceleration is going to be v squared over r. No mass for this one. Well, how do I figure out the velocity? Well, the velocity is going to be distance divided by time. The distance is 2 pi r divided by time. Time, I'm using capital T because it's the period of circular motion. So if it makes one loop around, it travels the circumference, and then it takes that long to travel the circumference. Okay, I can do some simplifying here. So I'm going to get 4 pi squared r squared divided by r is going to just be 1r divided by t squared. Okay, so 4 times pi squared times the radius is 1.5 times 10 to the 11 divided by the period, which is this number, 3.15 times 10 to the 7, and then squaring the whole thing there. So we are going to get 0.00597 meters per second squared. That's a little number, and that makes sense because it doesn't travel around very fast. Hey, looking at the next one, what is the gravitational force acting between the Earth and the Sun? Another easy question. F is equal to ma after all. Well, I know the mass of the Earth. It's 6 times 10 to the 24. I know the acceleration of the Earth. It's right there. So 0.00597. Multiply them together. We are going to get 3.58 times 10 to the 22 newtons. Done. What is the mass of the sun? All right, doing some gravity here. G, big M, little m over r squared. Alrighty, I know the force. I figured it out just a second ago. So 3.58 times 10 to the 22. And that's going to equal 6.67 times 10 to the negative 11 times big mass of the sun, which I don't know yet, times 6 times 10 to the 24 for the Earth, divided by the radius of 1.5 times 10 to the 11. Square that. Solve, solve, solve. M is equal to 2.01 times 10 to the 30. And that is actually true. More or less, depending on rounding. All right, easy stuff. Let's do some other things. A amusement park ride consists of a large cylinder and rotates around the central axis. The passengers stand against the inner wall of the cylinder. Once the passengers are moving at a certain speed, we'll call it V. The floor on which they are standing is lowered. Each passenger feels pinned against the wall of the cylinder as it rotates. Let R be the radius. Okay, so everyone is inside of this shape, and they're being pressed up against the wall as it's spinning around. So fun. Draw and label all the forces act on the passenger of mass m as the cylinder rotates and the floor lowered. All right, let's just draw the guy against the wall here. So here's the person. There's the wall, and they're spinning around like we have in that other picture. So what kind of forces are there? There is gravity. We'll call it Fg. What else is there? There is a normal force right here. So we'll call it Fn. And there is a frictional force. We'll call it Ff. All right, that is it. These are not balanced forces. There is no force here. There is no force here because you are accelerating that way in the normal force. You're accelerating towards the center of the circle. So that is the normal force. Ta-da. Okay. So now describe what conditions must hold to keep the passengers from sliding down the wall of the cylinder. Okay, so we're going to figure out how fast you have to go basically here. So I know what the force of gravity is. Force of gravity is mg. That means the force of friction must be also equal to mg. All right. Ta-da. But I don't want to worry about it that way. The force of friction is mu times the force normal. Okay? So I know that mg is equal to mu times the force normal. But the force normal, I can figure out what formula that is, because the force normal is going to be from the centripetal motion here. So that is going to be m times v squared over r. Okay, fun stuff. Cancel out those m's. Bada bing, bada boom. All right, so what conditions must hold? Well, which one's got to be bigger? Well, this force must be greater than or equal to. If they're equal to, great. If it's more, if this side is more, awesome. If this side is less, you're gonna have a bad time. All right, I guess we can rewrite it to make it look a little prettier at least. Beauty is in the eye of the beholder after all. And we want to make it as easy for them as we can. Mu v squared over r. Nice. Okay, compare the conditions discussed here for an adult passenger of mass m and a child of mass m over 2. It does not matter. Mass does not matter, which is ironically stated, but either is going to be okay. Everyone will fall down at once or everyone will not die at once. Either situation, as long as they got the same stickiness to their clothes. You wouldn't want to wear your silk pajamas, I suppose, when you're doing this. All right, let's do the next one. A curved section of a highway has a radius of curvature r. Must be the pirate road. The coefficient of friction between the standard automobile tires and the surface is mu. Draw and label all the forces acting on the car of mass traveling along the curved part of the highway. Okay, so you're driving down the highway, maybe looking for a show. You're driving this way. Nice. So here's your car. There's the surface. Here's your tires. Your budgeting's not quite good enough for the multicolored yet. Now, what we have, all the forces. We've got this force here, which is force of gravity. We've got this force here, which is force normal. We've got this force here, which is force of friction. Your force of friction is your centripetal force, which is pointing towards the center of that circle there. Nice, nice. Got them there. Compute the maximum speed with which a car of mass m could take a turn without skidding in terms of, oh, that's probably a mu. R, G, and M. Nice, nice. So what's the highest speed we can take? Well, what's the highest speed we can take? We know the friction force is going to match the centripetal force, right? Is equal to centripetal force, because it is the centripetal force. All right, so we have mg, which is the normal force, times mu is going to equal mv squared over r. Nice, nice. Cancel out those m's. So the highest speed is going to match mu gr equals v, and let's just go ahead and square root it. That's it. So the highest speed you could take is the square root of mu gr. Let's think about it. Does it make sense? If you had a bigger friction, could you go faster? Yep. If you had a bigger radius, could you go faster? Yep. If you had bigger gravity, could you go faster? Yep. Nice. So these city engineers, I thought they were driving the trains, are planning on banking the curved section of the highway at an angle of theta. How smart of them. I would bank on that, doing better. Okay. Draw and label all the forces acting on the car of mass m as it's there. So here's our fancy car. And it's got tires. Ah, good old tires. Draw and label all the forces acting on it. Do not include friction. Ooh. Okay. So we're driving in winter. What kind of forces are here? You've got force of gravity. You've got a normal force. Force normal. Nice, nice, nice. And that's it. There's no friction here. Making it too easy. Okay, the engineers want to make sure the car of mass m traveling at a constant speed v, which is, of course, supposed to speed limit, and everyone would always travel at that speed or below, could make it safely around the bank turn even if the road were covered in ice, essentially frictionless. How about legitimately frictionless? Compute this banking angle in terms of those letters there. All right, so we're solving for the angle. All right, let's split it apart. There's two forces in the gravity that we want. We want this guy here and we want this guy here. This guy is going to be the mg and, oh, hold up. I'm doing it crazy. Who wants to do it that way? Let's do it this way. This is what we love, right? So this guy right here, the normal force, is going to be mg cosine theta, but I don't actually care about that. This one right here is going to be the mg sine theta. Nice. So that's the force that's pulling it down there, right? So I want the centripetal force, which is going this way, to be made, oh, maybe I should start using a different color here. Centripetal force, which is going to be right there, is going to be made of two forces. It's going to have the force normal, and it's going to have this force here. This force, of course, is going to have to equal that mg sine theta, all right? But to keep it easy, let's not think of it like that. let's think of it, this is your right angle here, let's think of it as coming from the force centripetal. Is it going to be the sine or cosine? Oh, let's think about it here. Here's your theta, that's going to be the theta there, right? Because if you kind of like reflect it over this line here, then the triangles line up, because the right angles line up there, and the hypotenuses line up. Hypotenuses. So this guy is going to be your force centripetal times the sine. Sine? Oh, we put the angle in the wrong place. I'll show you how we know that. Because if I draw this vertical line here, this is a theta, right? So that means that this is a theta there, right? And this is a 90 degrees. So bada bing, bada boom. If this is a theta, and these are parallel lines, and that's a transversal, that's going to be a theta. Not that one. Sorry about the mess. But anyways, what it boils down to is that this is going to be a cosine theta, not a sine theta. All right, got that mess out of the way. Yeah, read it more carefully than I do. These two things are going to be equal. So let's set them equal to each other. So we're going to have mg sine theta coming from here is going to equal your force centripetal cosine of theta coming from there. But we're going to plug in what's the centripetal force here. So we're going to have equals mv squared over r cosine theta. All right, and this is the same. So let's try to simplify some things. One thing we can simplify, boom, boom, there goes the mass. We're solving for thetas, but there's two thetas. Oh, but wait, there's a sine and a cosine. Oh man, are you feeling it? Are you feeling it? I hope so. So we're going to divide everything by cosine and kick the g over to the other side. So we're going to have sine theta over cosine theta, which is your old friend, the tangent. Yes, he snuck out of the dark. You didn't see him there because he's so tan. We're going to have v squared over rg. Nice, nice, nice. So solving for theta, which is what we were looking for, right? Yeah, that's going to equal inverse tangent arctan of v squared over rg. Nice, easy stuff, except for drawing that purple triangle. How about that, huh? Okay, hopefully you had fun. We'll see you tomorrow for the next day, whatever number that was.